True. Glasses in the box here, glasses in the box right here. If you don't have a, what do they call them? A pair of glasses. There's one glasses. What do they call it? A pair of pants. Glasses, 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 glasses. If you don't have them, come down and get glasses. All right, we'll get started here. So the glasses, just hold on. We're gonna use those to introduce chapter 6. We're gonna get it as dark as possible in here. All the lights are going off, all the screens are going down. So hold on to those glasses until we get to it. Let's see, we've got 6 for a quiz question here. Yeah, 6. Let's see what we got. 5 liters of water. So 5 liters would be 5,000 milliliters. And the density of water is 1. So this would be 5,000 grams. So a person tries to heat up about add 5 liters of 80-degree water to 60 liters. So this likewise, if that's 5,000 grams, this would be 60,000 grams. So we'll do Q lost, Q gain, of course. And what's going to lose heat, of course, is the 80-degree water. So that's going to be 5,000 grams. Now, the specific heat of water, it isn't going to matter. It's going to cancel out. So I'm going to put in 1 calorie per gram degree Celsius. And then the temperature change for that hot water, it's going to go from 80 to 30. No, what is the final temperature? I'm sorry, final temperature. That's going to be 80 minus T final. Right? It's going to be less than 80 when we're all done. If that 80-degree water goes into 30-degree water. And on this side, we're going to have 60,000 grams. And the specific heat, 1 calorie per gram degree Celsius. And that's going to be T final minus 30. I didn't even solve that for T final. What for T final? Yeah. But the specific heat cancels out on both sides, all right? So you can solve that for T final. That should go pretty rapidly. All right, number 8. Okay, what do we got here? All right, so we have to take H2O liquid at, we're going to freeze this to ice, and then we got to lower the temperature of the ice as well. But we're going to have H2O liquid at 85. We have to go to H2O liquid at 0 degrees Celsius. So we know that portion right there is going to be MC delta T, right? For that portion. Then we have to take it to H2O solid. We have to freeze it at 0 degrees Celsius. So that is going to be the mass times the enthalpy of fusion. Then we need to take that and lower it by 5 degrees. So we're still going to have H2O solid. And that's going to be MC delta T. We know that this, though, has to be specific heat for ice right there, right? It has to be the specific heat of ice. So you'd have to add those three up. We'd add those three up. All right, 15 and 16. All right, so 15. Okay, so we've got oxygen gas here, and we've got oxygen gas here and oxygen gas here. Carbon monoxide is right there. And then CO2. It looks like we got to reverse this one times 2. Second one, reverse times 2, because of there's a 2 here that we need to obtain. And the CO2 gas is on the product side. We need to get that switched around, right? So this should be reverse times 2. And the other one is going to be what? Times 2 reverse. Wait. This one's only times 2, right? We don't need to reverse it. The top one, we need to reverse times 2. That should be times 2. Yeah, and the top should be reverse times 2. Times 2 on the bottom one, reverse times 2 on the top one. Yes? Somebody's got this worked out? Thumbs up, yes? Yes, okay. And then 16. What do we got? We got N2 N2's right there. That looks good. Somebody should be happy about that. Whoa, we've got O2, O2, and NO, and the NO is right here. It looks like, don't we have to just reverse the second one? That's it? Don't even have to multiply it, do we? We can just reverse the second one, yes? Okay, it looks like we just should have to reverse the second one here. Reverse the second one, add them together, you should have it. The way it looks, huh? Okay, so now let's finish off where we're at, which is the bottom of page 15. So we're going to finish up pages 15, 16, and 17. So we got about 3 problems to do, and then that'll do us. So we are continuing to do Hess's law, where we are adding reactions to obtain the one that we really want to study. And reminder, you would do this if you had a dangerous reaction that you didn't run, you didn't have the right materials to run it, or it just takes too darn long. So I think we've got everything highlighted here. Now, one thing you haven't seen me do, you could divide these as well. So let's see what we get here. So no, I always start with the third one, because then it just, if you start with the bottom one, you're not crossing your arrows. So the bottom one, we need to reverse that. Yes, we need to get chlorine trifluoride on the other side. So it looks like number 3, we need to reverse this baby. Now, again, I've done this problem 3 or 4 different ways. So this is not the only way to do it. So if we reverse this, we're going to have 1/2 Cl2O gas plus 3/2 OF2 gas. And we're going to get ClF3 gas. And delta H then is going to be, am I on the screen yet? Yes, negative, correct? We got to change the sign. If we reverse it, we're changing the sign, negative 266.7 kilojoules per mole. Okay, so we reverse that. How about reaction 2? What do we got to do? All we're doing is what's in yellow. We're looking at what's in yellow. We're going to divide that by 2, yes? Or multiply through by 1/2 is the same thing. So reaction 2 times 1/2. Right? Because we need to get this 2 down to a 1 for the CLF. So if we do that, I'm going to have 1/2. I'm going to put it in red. We've got 1/2 2 CLF gas plus 1/2 O2 gas gives us 1/2 Cl2O gas plus 1/2 OF2 gas, and then delta H is going to be 1/2 of, am I still on the screen? Not quite, no. 205.6. So I have my red 1/2 went all the way through, correct? Multiplied everything through by 1/2. So then I'm going to get half the amount of energy output, or input in this case, because it's positive. Now let's, what do I got to do to reaction 1? We're going to reverse it times 1/2. Yes, we got to get this 2F2 on the reactant side, and we got to get rid of this 2 because there's no 2 in the reaction that we want here. So reaction number 1, we are going reverse times 1/2. All right, so I'm going to end up with 1/2 2F2 gas plus 1/2 O2 gas. It's going to yield 1/2 2OF2 gas. I'm going to pull my highlighter back out just to, there's such a mess of this. So let's see, make sure I need F2 wherever it is, right here. F2, is there F2 anywhere else? No. F2, CLF, CLF, and then CLF3. That means anything I didn't highlight has to cancel out. So we need the same exact thing on the reactant side as on the product side, right? So whatever I did not highlight has to cancel out. All right, let's see what we got here. This is 1 OF2. This is 1/2 OF2. So I'm going to circle this in green here. 1/2 OF. Here's my OF2 is the same. This is 3/2 OF2, right? This is 1, 1.5. And that's going to cancel out right there. That's going to cancel out. Then the 1/2, this 1/2 Cl2O gas should cancel out right there. And then what am I missing? Why is my O2 not canceling out? What did I screw up? I forgot O2 in the top equation. Oh, crap. Yes, I did. So when I reverse this, this O2 right here, I forgot. That O2 right there, I forgot. So this O2 that I now put in there, that O2 there is a full O2 is going to cancel out with a half O2 and the half O2. And we should have it. We should have it. 1/2 times 2 CLF is CLF. 1/2 2F2 is F2. And CLF3. We should get negative 39, 139.2. That one's kind of ugly. That one's ugly. There's other ways to do it. Again, I've done this 4 or 5 different ways. I've multiplied. If you take this first one and multiply it by 2, I mean, that's the tendency in math. Get rid of the halves, take the first one, multiply it by 2. You could solve it that way as well. So again, this is not the only way to solve this. Okay, let's go to the last 2 problems or so. All right. Now we have a new wording a little bit. And this is enthalpy of formation. So you'll see it this way with an F. So the standard enthalpy of formation is the enthalpy change for a reaction in which exactly 1 mole of pure substance is formed from free elements in their most standard states under standard conditions, which is close to room temperature, 25 degrees Celsius, and 1 atmosphere of pressure is kind of normal pressure. 1 molarity solutions, if we're talking about solutions. And then, is their most standard state a solid, liquid, or gas? Mercury at 25 degrees Celsius at normal room temperature. What is mercury? It's a liquid, correct? What is oxygen in the most standard state? It's a gas, correct? What is gold in the most standard state? Solid, right? So the enthalpy of formation values for the elements in their standard state is 0. So it is the heat energy needed to make 1 mole of the pure substance from the free elements. So then there's a table of enthalpy of formation, and whether or not you have a solid, liquid, or gas matters, because here's H2O liquid as soon as this thing decides to focus. So there'll be a table of enthalpy of formation values like this. Notice oxygen is 0. O2 gas that we breathe in that's oxygen. What is the most standard state for carbon? It's pencil graphite, so it's 0. Okay. Most enthalpy of formation values are negative, indicating that formation from the elements are exothermic. Now, how do you do this? To calculate this, this is my summation, right? That's a summation symbol for in mathematics. This is my moles. And then it is the enthalpy of formation of products minus big minus enthalpy of formation for reactants. Products minus reactants. And the best way to do this is just to do the next example right away and you'll understand it. Okay. It says using the enthalpy of formation values, which are on the bottom right here a little bit, right here. Now, remember, this is products on this side and reactants on this side. So using enthalpy of formation values, what is the standard enthalpy change for this reaction? So we got to sum up the products minus reactants. To sum up the products, I'm going to go down here. I'm going to go straight across. And I'm going to make a big bracket here. This is where I'm going to start my products. From the balanced equation, it is 2 mole HNO3 aqueous then how much heat energy is needed to make HNO3 aqueous? It is negative 207.4 kilojoules per mole. Plus, how many moles of nitrogen monoxide? What number's right there? A 1, correct? 1 mole of NO gas. And what does it take to do the NO gas? $90.25 kilojoules per mole. I'm going to close this bracket. That would sum up my products, right? I'm on the right. That's my products. So that's my product. This is my sum of my products. I need this subtraction sign right here yet. We're going to subtract. I'm going to put a big subtraction sign right there. Products minus reactants. Now I'm going to do the same thing for the reactants. So I'm going to do my bracket here. And On the reactant side, I've got 3 mole of NO2 gas. And from the table on the right, 33.2. Plus 1 mole H2O liquid up there. Is it H2O? Yeah, H2O liquid. 1 mole of H2O liquid here. And negative 285.83 kilojoules per mole. We'll close this bracket, right? Products minus reactants. And product side, you can do this all with your calculator. You can probably use I would use a parenthesis in my calculator maybe, but minus 324.55 kilojoules minus minus 186.23 kilojoules if you did it separately. Products minus my reactants. Obviously, then we end up adding this, so the answer should be about 140 or so. And it's negative 138.3. Kilojoules. Exothermic, right? Negative. Okay. Our last problem, and Al does one like this too. They want us to figure out what one of these values is that I have in green. It's going to give us the total, but we're simply figuring out what is the enthalpy formation value for one of them that was on the table. So in the last problem here, it says the standard enthalpy of formation for the following reaction was found to be negative 1125.2 kilojoules. What is the enthalpy of formation for NO2? This. Oh, I've got it up there. I'm sorry. It's right there. I put a question mark already. Man. This is what we're looking for, yes? Now notice one of the values is not given. And that would be the enthalpy of formation of hydrogen gas is what? 0. So if it looks like an element, it's hydrogen. Hydrogen similar to oxygen, it's O2. If it's not given, it's 0. Okay, let's see what we've got here. Same thing. I'm going to put a bracket here. Add my products. Two mole of NH3 gas. And my value for this is minus 45.91. Plus 4 moles of water. That's my two products. Big negative sign there. Let's do the same thing. My reactants. In my reactants, it is 2 mole of NO2 gas. That's what we're looking for, right? We're looking for X here, correct? We do not know what that is. Plus 7 mole of hydrogen at 0. Equals negative 1125.2 kilojoules. So if we do these two for the products, we get 2 times negative 45.91 plus 4 times negative 241.8. It's going to be a pretty big negative number. negative 1059.02 kilojoules minus 2x equals negative 1125.2 kilojoules. So my cheater's math, which is make a math teacher cry, I'm putting the 2x, negative 2x on the other side of the equal sign. I'm going to make it positive, yes. And I'm going to bring this to the other side of the equal sign and make this positive. So I'm going to end up with minus 1059.02 kilojoules plus 1125.2 kilojoules is equal to 2x. So if we subtract that, 66.18 kilojoules is equal to 2x. So 33.09 kilojoules. So that's all there is to finish up. Hopefully you've cranked all of it out, except for maybe this is the last section, the last little bit, right? Okay. So that gets us to our meeting on Thursday. Now, our meeting on Thursday looks like this. So now you know, coming in, your bubble sheet is going to have your name on it, right? Typed in already on it. I'll try to lay them out. You're going to grab that. You're going to get an exam. Page 1 is going to have the number in this box. You're going to have some kind of ID. Now, if you don't have an ID, stop over there. It takes 30 seconds to get a photo ID that is free, right? Maybe you want to get a photo ID. Bring a driver's license. I don't know. Seat number doesn't matter. This is the outline of the questions. For sure, I've got this narrowed down for you, for sure. So if you look at your take-home quizzes and your learning guides, you will find a reaction that it starts out with moles and wants grams. You'll find more than one. You'll find reactions that have grams in it, and it's a limiting problem. You'll find a percent yield problem. You'll find an empirical formula problem burning a hydrocarbon. You'll find something to do with molarity, the dilution formula, pH of a strong acid or base, pH, BOH, reaction molarity, reaction molarity, reaction molarity, just what you just did in lab, right? You might have to figure out how many milliliters of something would neutralize some concentration of something else, a molarity, correct? You're for sure going to calculate a molarity just like in lab for your unknown acid. So there's 3 molarity stoichiometries, if you will. Specific heat where you got to calculate the final temperature. Looks like you got to find the specific heat of a metal. Another specific heat final temperature calculation. Heat needed for a phase change involving ice and water. We've done those, correct? In fact, we just did one of those on the quiz where you had to get the ice to -5, correct? Reaction, enthalpy of reaction. Hess's law, 1 reaction, 2 reactions, 3 reactions. You've got plenty of examples of them on the learning guide and on the quiz. And then a calculation like what we just did. That's outlined right there. That's it. I kept it multiple choice. It doesn't make it easier because the wrong answers are there, right? The wrong answers are there. Now, hopefully, what you should be doing is you should get done with that test in 30 minutes. Then you should go back and redo them. Don't change your answer, right? But you really should be trying to go through it rapidly, then come back and solving it from scratch. Don't look at your previous work. Put your hand over it if you have to, but don't look at your previous work. So here's what's on there. But I think I've got them in the questions too, like specific heats are probably listed in the questions. I don't think you're going to look at this reference sheet at all. I don't think you're going to look at it. I really don't. But this was the one I was given by my boss and said, you're going to use these things on the test. I said, okay, yeah. Like I said, I don't think you're going to look at that. So, okay. Let's talk about the next chapter then. So the next chapter, chapter 6, looks like this. And this starts out with electromagnetic spectrum. So Professor Dave, that's a YouTube video. James Clerk Maxwell, 1864, developed his theory of electromagnetic radiation and showed that light was the visible part of a vast spectrum of electromagnetic waves. These waves travel through a vacuum at a constant speed, symbol C, of 2.998 times 10 to the 8 meters per second. Waves are characterized by, this is an upside down, backwards Y, if you will, Greek letter lambda, which means wavelength, the distance between waves. I'm going to change this because I cannot deal with this. F, change this to frequency, F. Mu for frequency, and amplitude. The equation to calculate the speed of light is C is equal to lambda F. Now, I'm going to come back to this, but let's look at what we were talking about on page 3. So on page 3, you can look at it this way, or we can turn it sideways. And if we turn this sideways, and we kind of look at the top of the wave, that gives you the wavelength. Down here on the left end, we have a large wavelength. There's a big distance between the waves, yes? What type of waves have a long or large wavelength? Radio waves. Now, all of these waves travel the speed of light. Very fast. Then, oh, do you see any radio waves? You've got 94.1 on your radio, and then or there's another car driving next to you. They have their radio on because you can see it in there. You see that wave coming into their antenna? Next wave is microwaves. You put something in the microwave, hit the button. Do you see those waves zapping your food? Now, as the wavelengths get shorter, we go to infrared, IR. Now, back in the old days, you had to get your ass off the couch to change the channel on the TV. Yes. Back in the old days. Then you know what? They got a corded plug-in remote. And then somebody would trip over the cord and rip the cord out. And then you really could sit your butt on the couch, because then you got an IR remote, infrared remote control. Yeah. Now we don't even have those anymore, because our remote control goes through our network in our house. So we don't have to point that sucking thing straight at it. But if you hit an IR remote, you don't see that beam go into your TV. Now, this is the only waves that you see, visible light. These are the only waves that you see. These waves have a certain wavelength and a certain frequency. Now, if we look at this, red, orange, yellow, green, blue, violet. What the hell happened to indigo? Indigo kind of went the same as the planet Pluto, which isn't a planet anymore. I had to search the internet and search the internet and search the internet for lonely old indigo right here. Used to be Roy G. Biv, yes? Well, now it's just Roy G. BV. And this is what I found. Modern physics generally accept a 6-color spectrum. Indigo is omitted because few people can differentiate the wavelengths well enough to see it as a separate color. Okay, whatever. But again, this is the only thing we see from all these electromagnetic waves is this light. Then we got ultraviolet. You're outside in the sun, you're getting burned. You see those waves whacking your skin? Probably not, huh? Then we get up to X-rays and gamma rays. Now, as we go this way, as we go to the right, my wavelength gets less and less and less. But what gets more and more and more? Frequency. Frequency. Now, as we go up this way, this is what Al does in the beginning. As we go this way, look at my time. Frequency increases. If frequency increases, energy increases, wavelength decreases. Energy and frequency go together. Energy and frequency go together. What is the highest energy light? Violet. If you see something that's glowing red hot, that's not as hot as something that's blue hot. Temperature goes with the colors. The higher the frequency light, the more energy it has. The higher the frequency, the shorter the wavelength. Now, let's fill in this table. We know that C is equal to lambda F. I said, pretend the speed of light is 24. If my wavelength is 2, what's my frequency? If my wavelength is 2, my frequency is 12. Yes? These two better multiply together to get 24. If your wavelength goes up to 8, as the distance of the waves get bigger, what's my frequency going to do? going to get smaller. No matter what, if you change the wavelength, your frequency has to change because you cannot change the speed of light. If my frequency is 6, my wavelength is 4. If my frequency is 24, my wavelength is 1. And if my wavelength is a half, my frequency is 48. Now, we're going to calculate some frequencies of, perhaps some of you listen to 92.9, the X. I listen to the X once in a while, especially if somebody's got a country song, like I woke up on the wrong side of my truck bed and people love me as much as I love my truck. So then I can't deal with that anymore. I got to turn it over to the X. Yes. Country song, pickup truck, dog, beer, lady. But the pickup truck's not in there, the tractor's in there. Huh? Oh, wait a minute, we gotta break up. I forgot the love part of it, the girl. Girlfriend, dog, pickup truck, beer, I've got it right there. Okay, I want to make sure we get this in. Now, I want to show you this to prove these colors. We're going to look at these colors, and I got a page in. You do not have to page there. We are going to see colors like this. I'm going to show you with the glasses there. If you just look at this, all the reds are down here. Low energy light down here, higher energy light here. Now, you've heard somewhere along the lines that there is sublevels or shells of atoms, correct? Now, if we put energy into the atom in the form of electricity, heat, or light, it will absorb that energy. But that electron that gets ejected farther away from the nucleus is going to come back down. Oh, crap, I've had this on. We're going to eject that electron away from the nucleus with 5,000 volts. Somewhere, output 5,000 volts. If you want to start your heart back up, come on down here and just put your fingers in the ends here. Okay, if you look at my bulb that's in there, there is no filament in there. This is a gas discharge tube. This is simply helium. This 5,000 volts is going to eject those electrons further away from the nucleus. They are still attracted to the positive nucleus. They're going to come back down. The electrons that come back down, you only see color when they drop back down to energy level 2. I'll repeat, you only see color when the electrons drop back down to level 2. A big drop is going to have big energy. A small drop is going to have small energy. What's a small drop? Red light. Low energy light is red. When the electron drops back down from energy level 3 to 2, we get red light. A big drop, energy level 6 here is energy level 6. Dropping back down to 2 gets us this purpley color. You will see these colors. Big drops, bigger energy. Bigger energy, bigger frequency, lower wavelength. Okay? Now, so in order to see this, we need the room as dark as we can get it. Okay, so let's see. Do I have this? Remember which one I got. I'm gonna kill these lights. I'm gonna kill the screens. It's gonna get dark in here. I'm gonna get my flashlight ready on my phone. I'll put my fingers in that socket or something. And... Okay. Now, can I kill this screen if I put it behind? I don't think it's gonna matter. I think it's gonna work. All right, look at this with those glasses on. Remember what we're looking at. Oh, yes. Oh, that is a beautiful, perfect teal color, my favorite teal color. Yes. Who needs glasses? Who else needs glasses? Who else in here needs glasses? What's my LED on my phone look like? Is it working too? Yeah. Okay, now, what you see, well, I better put some glasses on. So what the heck is here? Okay, so again, you see a dark red, yes? To the right, dark red. Low energy. That red is a drop from energy level 3 to energy level 2. Then you see an orange. That drop of orange, I don't know if it's 3 dropping down to 2. Then you see a teal, and then you do see a violety purple color, yes? So this is all, you see those colors from the electron absorbing energy, boosting the electron further out away from the nucleus, and the negative electron is still attracted to the positive nucleus. So it'll drop back down and give the energy back in the form of light. Low energy light is red, high energy light is violet or purple. Okay. I have no idea what this looks like. If you really want to have a party, what you do is you put this thing on a spinner. And then you got all this stuff going on, right? Put this on a spinner, and then I won't say what else you probably need for your party to really get wild. Like, okay, so, whoa, I lost my flashlight. Come back here. Oops, lost my glasses and my flashlight. I'm like really blind right now. Why did my light go? All right, so that was, all right, so that was helium. Now, we can look at the stars and we can see these colors because fusion involves hydrogen and helium. This sucker's hot. Now, I'm going to switch this to hydrogen. This was what scientists were studying and really, really looking at was the spectrum for hydrogen. Four colors. Do we have 4 colors? 4 brighter colors? I don't know. This is not as nice as helium. I'm not very straight on. I'll move this. First color to the right or left is what color? What color do we get, right or left? We get a red. Okay, so again, you are seeing these colors. Each color has a certain frequency and a certain wavelength. Why do you see the color? Because the electron has absorbed energy. The electrons around these gases, in this case, it is hydrogen. Hydrogen only has 1 electron. It has absorbed the energy, went farther away from the nucleus, that negative electron still attracted to the positive nucleus, it comes back down. It's no different than gravity. If you throw a ball up, it's going to come back down. If you throw it higher, it can come back and hit your head and put a bigger lump on your head because it has more energy the higher it goes. The electron has more energy, similar to throwing that ball up higher. And when that comes back down to energy level 2, a high energy light will be high energy light will be violet or purple. All right, let's see. Light this place up again. That does get nice and dark, doesn't it? Okay. So I have just proved to you electrons, huh? Suspended in space like magic, yes? Y'all want to have a party now? I know. You should put a strobe light on and try to play pool with those glasses on. Playing pool with those glasses on, flashing. You only see a flat. You only see the pool balls if it's dark in there when the flash strobe lights, huh? Okay. We're powering on. What time we got here? We got a few minutes. Good. All right, we're coming back here. We're powering on. We're coming back. We hit that button. We've got power. We've got lights. We're back. Okay. I need screen. Then for this recording, I forgot to put the glasses. You can put the glasses in front of this and the people, yeah, I blew it. That's all right. Come to lecture. Then you don't have to worry about it. Okay. So let's see what we got here. Let's do this calculation though. To give you an idea of the difference in wave characteristics, you may listen to 92.9 the X for an FM station. M, it is in megahertz. FM is in megahertz times 10 to the 6th, or 790 kilohertz, WAYY for an AM station. That's talk radio or sports radio talk. Or you may use 4G cell signal, 700 megahertz. FM stands for frequency modulation. AM stands for amplitude modulation. The frequency in hertz of 92.9 is 92.9 times 10 to the 6th. And the frequency of hertz of 790 is 790 times 10 to the 3rd. This times 10 to the 3rd, that's the kilo, correct? And my 10 to the 6th, that's the mega. Therefore, the wavelength of 92.9 in meters. Okay, let's do that right here. We know that C is equal to lambda F. We want the wavelength. So I'm going to take the speed divided by my frequency to get me my wavelength. The 2.998 times 10 to the 8th meters per second. We're going to go 3 times 10 to the 8th meters per second divided by 92.9 times 10 to the 6th. Now, frequency is in hertz, which is 1 over seconds. And I'm going to put seconds to the minus 1. That's 1 over seconds. If we divide that out, we are going to get 3.23 meters. 1 meter, 3.281 feet. So the wavelength is 10.6 feet for FM 92.9. Wavelength. Okay. 790 AM. 3 times 10 to the 8th meters per second again, divided by 790 times 10 to the 3rd. $380 meters. $1,250 feet. AM radio wave, almost a quarter mile there before the wave repeats. What travels farther, AM or FM? Can you listen to an AM radio station farther away than an FM station? Oh, for sure. You could pull Chicago if the weather and everything is right. AM is much more affected by electric fences, atmospheric conditions, but AM a lot farther. So if we fill this in up here, meters through 3.23. And 10.6 feet. And 790 was 380 meters, 1,250 feet. Now, after your screen sharing is paused, well, apparently I screwed something up. After you ace the test on Thursday, start poking around in OWL in chapter 6. And then what it really does, it does a lot of this. Frequency and energy go together. Frequency and wavelength are going to be opposite of each other. So you can go and poke around in the OWL. On your way out, put the glasses in this box here. Somehow get the glasses to this box right here. And then we'll see you on Thursday.